Far beyond the reach of our solar system, something strange is happening in the darkness. A new study has dropped less than 24 hours ago and is changing everything. We now have proof that 3I-ATLAS isn't just gliding silently past the stars, it's shifting, pulsing, like a cosmic heartbeat locked to an invisible clock. Indeed, scientists in Russia have now confirmed it. A repeating rhythm, too precise to dismiss as chance, too regular to ignore as chaos. Is this nature's perfect metronome, or the echo of design? Tonight, we'll peel back the layers of this new data, step by step, signal by signal, until the patterns reveal themselves. Stay with me until the end, because what we uncover may change the way you see not just comets, but the possibility of intent in the cosmos itself. If this mystery has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about 3I-ATLAS. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. Russia breaks the silence, a shocking first move. Picture this. It's October 8th, 2025, and somewhere in a Russian observatory, two astronomers are staring at data that doesn't make sense. Yuri Medvedev and Sergei Pavlov have been tracking a visitor from beyond our solar system, a comet designated 3I-ATLAS, and what they're seeing shouldn't be possible. They run the numbers again, then again. The pattern holds, and so they do something that will echo across every space agency on Earth. They publish their findings in Astronomers Telegram number 17437, and the world of astrophysics quietly begins to fracture. What did they find? The comet is shifting, not drifting, not tumbling through space in the chaotic way comets usually do, but shifting with a rhythm, a pulse. Every 4 hours, give or take 2 hours, its position changes in a predictable pattern. Every 2 hours, with a margin of about 1.33 hours, its brightness surges and dims. These aren't approximations or wishful thinking. They use something called a Lomskagel periodogram, a statistical tool so precise it can find hidden rhythms in seemingly random data, the kind of tool you use when you're hunting for patterns that nature doesn't usually offer. Now here's where it gets strange. Russia announced this, openly, publicly, while NASA, the Chinese National Space Administration, and the United Arab Emirates space program have said nothing. Radio silence from the agencies we usually hear from first. Some might say it's bureaucracy, or maybe a government shutdown that's tied up data release. Others might wonder if there's more to the story, if someone decided this information needed a softer landing or no landing at all. But Russia didn't wait. They broke the silence, and now we're all left wondering what everyone else knows that they're not telling us. This isn't just about scientific protocol. This is about who controls the narrative when something arrives from interstellar space, behaving in ways that make experienced astronomers pause. When Oumuamua showed up back in 2017, it took weeks for the scientific community to even agree on what it was. A rock? A comet? Something else entirely? And by the time we had our telescopes pointed the right way, it was already leaving. But 3I-ATLAS? We've been watching it for months now, and the more we watch, the less it behaves like anything we've catalogued before. The Russians aren't known for making wild claims in astrophysics. Their space program has a reputation for rigour, for double-checking, for not publishing unless the math is solid. So when Medvedev and Pavlov put their names on a telegram that essentially says, this object is doing something regular, something predictable, something that looks almost deliberate, the global scientific community has to pay attention. Because comets don't do regular. Comets are chaos engines, spewing gas and dust asymmetrically, tumbling through the void with all the grace of a broken washing machine. Think about what regularity means in space. Our solar system runs on regularity. Earth orbits the Sun every 365.25 days. The Moon pulls our tides in predictable cycles. Pulsars spin with such precision we can use them as cosmic clocks. But these are established systems, objects that have settled into their rhythms over billions of years. 3I-ATLAS is a visitor. It came from somewhere else, somewhere beyond the bubble of our Sun's influence, and it arrived spinning like a metronome. That's not normal. That's not what interstellar wanderers do. So, what are the alternatives here? Either this comet has a shape and composition so perfectly balanced that it naturally rotates with machine-like precision, which would make it a 1 in a billion geological fluke, or something about its structure or origin is fundamentally different from every other comet we've ever studied. Or, and this is where the conversation gets uncomfortable for some scientists, it's doing this on purpose. That last option is the one nobody wants to say out loud in a peer-reviewed journal. Because once you suggest intentionality, once you open the door to the idea that an object from interstellar space might be controlled, you're no longer doing conventional astrophysics. You're doing something closer to archaeology, or first contact, and that's a field where reputations go to die if you're wrong. But the data doesn't care about reputations. The data just sits there, blinking its 2-hour pulse, waiting for someone to explain it. Russia's decision to publish might have been strategic. In the arena of space exploration, being first matters. It shapes how the story gets told, who gets cited, whose scientists become the reference point. By releasing this finding before anyone else, Medvedev and Pavlov put their country at the centre of what could become the most significant astronomical discovery in modern history. If 3I-ATLAS turns out to be something extraordinary, Russia will be remembered as the nation that told the world first. If it turns out to be nothing, well, they publish data. That's what scientists do. But here's the question that should keep you awake tonight. If multiple agencies have been tracking this object, and Russia is the only one talking about these periodic shifts, what does that tell you about what the others are seeing? Are they seeing the same thing and choosing silence? Are they seeing something different and waiting for more data? Or are they seeing something so strange that they haven't figured out how to tell us yet? Because in the history of space exploration, silence is rarely empty. Silence is usually full of people arguing in closed rooms about what the public needs to know and when they need to know it. And right now, while Russia speaks, the silence from everyone else is deafening. Warned Part 2. The dual signature. Positional shifts and brightness pulses. Let's talk about what these Russian astronomers actually measured, because the specifics matter more than you might think. When you track an object moving through space, you're essentially predicting where it should be based on gravity, velocity, and trajectory. You calculate its path, then you observe where it actually appears, and you compare the two. The difference between where you predicted and where you observed is called an O-C residual. Observed minus calculated. For most comets, these residuals are messy, inconsistent. Because comets are messy, inconsistent objects. They leak gas, they spin unevenly, they get pushed around by their own outgassing in ways that are nearly impossible to predict. 3I-ATLAS has O-C residuals that repeat. They cycle. Every 4 hours, with that 2-hour margin of error, the comet's position deviates from the calculated path in a way that matches the previous deviation. That's not how chaos works. Chaos doesn't have a schedule, and yet here we are, watching an interstellar comet keep appointments with mathematical precision. The brightness variations add another layer to this puzzle. Comets get brighter and dimmer as they rotate because their surfaces aren't uniform. One side might be icier, more reflective. Another side might be darker, covered in organic compounds or dust. As the comet spins, we see different faces, and the brightness changes accordingly. But usually these changes are irregular, or if there is a pattern, it's loose, approximate. The kind of pattern you might notice if you squint at the data long enough. 3I-ATLAS doesn't require squinting. Its brightness pulses every 2 hours with such regularity that when you plot it on a graph, you can practically set your watch by it. Now, the Lomskargel periodogram that Medvedev and Pavlov used is designed for exactly this kind of work. It hunts for periodicities in unevenly sampled data, which is what you get when you're observing a comet from Earth and clouds roll in, or daylight interrupts, or your telescope time runs out. Traditional Fourier analysis would struggle with gaps in the data, but Lomskargel thrives on it. It's the tool you use when you suspect there's a signal hiding in the noise, when you think nature might be trying to tell you something if you just listen carefully enough. And in this case, it found 2 signals, the 4-hour positional shift and the 2-hour brightness pulse. Here's where it gets mathematically interesting. The brightness pulse is exactly half the period of the positional shift. 2 hours versus 4 hours. That's not coincidence you stumble into. That's a harmonic relationship, the kind of ratio that makes physicists sit up straighter in their chairs. If the comet was shaped like a dumbbell, rotating end over end, You might expect to see it brighten twice per rotation as each bulbous end faces us. That would explain the 2-to-1 ratio. But dumbbells don't typically produce positional shifts with such precision. They wobble, they precess, they do complicated things with their angular momentum that should smear out any periodic signal over time. Unless, of course, the object isn't wobbling, unless something is keeping it stable, locked into a rotation that doesn't decay or drift. In engineering, we call that active stabilization. Spacecraft use reaction wheels and thrusters to maintain precise orientations. Satellites use magnetorquers and momentum dumps to stay pointed at Earth. But comets don't have thrusters. Comets are frozen chunks of ice and rock that formed in the outer reaches of some distant star system billions of years ago and have been coasting through the void ever since. They don't stabilize themselves. They can't. Except this one appears to be doing exactly that. Let's consider what we're actually seeing when we observe these patterns. The positional shift means the comet's trajectory is oscillating slightly, moving back and forth across its predicted path in a regular cycle. That could be caused by jets of gas erupting from its surface, but those jets would need to be firing with perfect timing, perfect symmetry, in a way that maintains the oscillation without damping it or amplifying it into chaos. Natural jets don't do that. Natural jets are erratic, sputtering, driven by sunlight heating different parts of the surface at different rates. The brightness variation means something on or about the comet is reflecting sunlight toward us in a pattern that repeats every 2 hours. If it's just the comet's shape and rotation, then we're looking at an object with an almost artificial symmetry, something nature doesn't tend to sculpt, without a lot of collisions and grinding and randomization. If it's not just shape, if there's something on the surface creating this effect, then we need to explain what natural process could produce reflective regions so evenly distributed that they pulse like clockwork. Some scientists have suggested we might be seeing a bilobed nucleus, 2 large chunks of ice connected by a narrow neck, spinning around their common centre of mass. That could produce a 2-peak brightness curve, but bilobes usually wobble. The famous comet 67P/Churyumov-Gerasimenko, which the European Space Agency's Rosetta mission studied up close, is shaped like a rubber duck, clearly bilobed, and it tumbles through space with a complex rotation that took months to fully characterize. It doesn't pulse with metronomic regularity. It dances a chaotic waltz. 3I-ATLAS is not dancing. It's marching. And that distinction, that shift from chaos to order, is what has some astronomers quietly worried and others quietly excited. Because order in nature usually has a cause, and the cause is usually simple once you find it. Planets orbit regularly because gravity is predictable. Crystals form regular patterns because molecular bonds have preferred angles. But what causes an interstellar comet to spin like a gyroscope and flash like a lighthouse? That's the question keeping researchers awake, running simulations, checking their instruments for errors that might explain away something they're not sure they want to be real. And here's the thought that should unsettle you as you drift off tonight. If this pattern is real, if 3I-ATLAS is genuinely exhibiting this dual signature of position and brightness with such precision, then either we're witnessing the most perfectly balanced natural object ever discovered, or we're witnessing something that was balanced on purpose. And if it's the latter, then someone has to ask the question nobody wants to be the first to ask in a serious scientific setting. Who balanced it, and why? Part 3. Precision in Chaos. Why comets shouldn't behave this way. Comets are not elegant objects. Let me be very clear about that from the start. They're dirty snowballs, frozen relics from the formation of planetary systems, collections of ice and dust and organic gunk that spent billions of years in the cold dark, waiting for something to nudge them toward a star. When they finally fall sunward and start to warm up, they don't do it gracefully. They leak, they crack, they develop jets of gas that shoot out asymmetrically from wherever the surface happens to be warmest. These jets push on the comet unevenly, creating torques that change its rotation in unpredictable ways. It's like trying to spin a leaky water balloon filled with gravel while someone keeps poking holes in random spots. The result is chaos, not clockwork. Every comet we've studied up close has confirmed this messiness. When the Giotto spacecraft flew past Halley's Comet back in 1986, it found a nucleus that was darker than coal, shaped like a peanut, with jets erupting from specific regions on the sunlit side. The rotation wasn't clean, the outgassing wasn't symmetrical. Halley's tumbles through space with a complex spin that takes about 7.4 days for one rotation, but even that's an approximation because the spin axis wobbles and the rotation period changes slightly each time the comet passes near the Sun. That's normal. That's what comets do. Comet Wild 2, visited by the Stardust mission in 2004, looked like someone had taken an ice cube and bombarded it with bullets. Craters and pits and flat-topped mesas covered its surface, evidence of impacts and erosion and structural failure. Its rotation was irregular. Its shape was lumpy. Again, this is expected. Comets aren't formed in factories with quality control. They're assembled by random collisions in the outer solar system, and they show it. Then there's 67P/Churyumov-Gerasimenko, the rubber duck comet that Rosetta studied for 2 years. We got to know that comet intimately, watched it up close as it approached. The Sun saw its jets turn on and off, measured how its rotation changed day by day. The comet's period varied by about 20 minutes during the time Rosetta was there. 20 minutes doesn't sound like much, but in the context of a 12-hour rotation, that's a significant shift. The comet was spinning down, slowing its rotation, because outgassing was acting like tiny rocket engines all over its surface, and they weren't balanced. They couldn't be balanced. Nature doesn't work that way. So when 3I-ATLAS shows up spinning with a period that doesn't seem to be changing, that doesn't seem to be wobbling or precessing or doing any of the things comets are supposed to do, we have to ask ourselves what makes it different. Is its shape somehow perfectly symmetrical? Is its composition so uniform that outgassing happens evenly all over the surface? Or is something else going on? The odds of a comet being naturally symmetrical enough to rotate this precisely are astronomically small. Think about how a comet forms. You start with a region of a protoplanetary disk, a swirling cloud of gas and dust around a young star. Grains of ice and rock stick together through static electricity and gentle collisions. Over time, these clumps grow larger, accreting more material, but the process is random. One side might accumulate more ice, another side more rock. The final shape depends on thousands of collisions, each one unique, each one adding mass in a slightly different place. The result is almost always asymmetric. It has to be. The probability of all those random collisions producing a perfectly balanced object is like dropping 1,000 coins and having them all land on edge. But let's say, just for argument, that 3I-ATLAS did form with some kind of remarkable symmetry. Maybe it's a contact binary, two similarly sized objects that merge gently, creating a dumbbell shape with each lobe roughly equal in mass. That could, theoretically, produce a stable rotation. But even contact binaries have irregularities. The net connecting the two lobes is usually weak, subject to tidal forces and structural stresses. Over billions of years coasting through interstellar space, you'd expect micrometeor impacts to chip away at the surface, creating new asymmetries. You'd expect cosmic rays to alter the ice chemistry, creating regions that outgas differently when the comet finally gets close to a star. Symmetry is fragile. Time erodes it. And yet here we are, observing an object that seems to have maintained its balance across light years of travel. It entered our solar system from interstellar space, which means it's been subjected to gravitational perturbations from the Sun, from Jupiter, from every massive object in our neighbourhood. Those perturbations should introduce wobbles, should change the rotation period, should do something to disturb the pattern. But according to Medvedev and Pavlov's data, the pattern holds. The 4-hour shift, the 2-hour pulse, they persist with a consistency that's frankly unnerving if you understand how fragile rotational stability usually is. Now compare this to Oumuamua, the first interstellar object we detected back in 2017. Oumuamua was strange in its own right, accelerating away from the Sun in a way that couldn't be explained by gravity alone, tumbling through space with a rotation period that changed our estimates of its shape every time we looked at new data. Some researchers proposed it was a flat pancake, others thought it might be cigar-shaped, elongated like a cosmic javelin. The point is, it was weird and irregular and confusing, which is what we expect from objects that have been wandering the galaxy for eons. It had been battered, randomized, left to spin however the universe decided. 3I-ATLAS is the opposite. It's not random. It's not confused. It's locked into a rhythm that seems immune to the chaos that surrounds it, and that immunity is what's driving some scientists to consider possibilities they'd rather not consider. Because in all the comets we've studied, all the asteroids we've tracked, all the natural objects we've catalogued, Precision like this is rare to the point of non-existence. Precision requires either extraordinary luck or extraordinary engineering, and luck doesn't usually show up with a 2-to-1 harmonic ratio and a Lomskargel periodogram that looks like a textbook example of a clean periodic signal. So tonight, as you think about 3I-ATLAS spinning through the void, ask yourself this: what would it take for nature to create something so precise? What sequence of events, what perfect storm of conditions, would have to align to produce a comet that behaves more like a satellite than a snowball? And if you can't think of a plausible natural explanation, if the odds seem too long and the coincidences too convenient, then maybe it's time to consider the alternative. Maybe it's time to ask if precision in chaos is nature's signature, or someone else's. Part 4. Natural models tested against the data. Scientists don't jump to exotic explanations when something unusual shows up. That's not how the field works. You start with the simplest, most mundane possibilities, and you test them against the data until they either fit or break. So when 3I-ATLAS started showing this regular behaviour, astronomers worldwide began constructing models, trying to explain the periodicity without invoking anything more complicated than ice and rock and physics. Let me walk you through what they came up with and why each model runs into problems. The first and most obvious hypothesis is the symmetrical nucleus model. If the comet's core is shaped like a dumbbell or a contact binary with two lobes of roughly equal size and mass, it could theoretically rotate around its centre of mass in a stable way. As it spins, we'd see each lobe once per rotation, and if both lobes are similarly reflective, we'd get 2 brightness peaks per rotation period. That matches the 2-to-1 ratio between the positional shift and the brightness pulse. So far, so good. But here's where it gets tricky. For this model to work, the 2 lobes need to be remarkably similar. Not just close, but nearly identical in mass distribution, surface composition, and shape. If one lobe is even slightly heavier, or has a different centre of mass, the rotation becomes unstable. The comet starts to precess, wobbling like a top that's running out of spin. Over time, this wobble would smear out the periodic signal we're observing. We wouldn't see clean 4-hour shifts and 2-hour pulses. We'd see variations, drift, the kind of messy data that characterises normal comet rotations. And there's another problem. Contact binaries usually form from gentle collisions in the outer solar system, where 2 objects merge at low speed. These collisions aren't surgical. They create irregularities at the contact point, stress fractures, regions of different density. When the merged object starts outgassing as it approaches a star, these irregularities matter. Gas erupts more strongly from some regions than others, creating torques that change the rotation period. We've seen this with every contact binary comet we've studied. Their spins aren't stable, they evolve. So the symmetrical nucleus model requires not just a balanced shape, but also balanced outgassing, which brings us to the second hypothesis. Maybe 3I-ATLAS has jets of gas erupting from its surface, in a configuration that maintains its rotation instead of disrupting it. Imagine 4 jets positioned at the equator, 90 degrees apart, each one firing with exactly the same force. As the comet rotates, these jets would push on it symmetrically, cancelling out any torques that might change the spin. It's like a rotating lawn sprinkler where the water jets create a torque that keeps it spinning at a constant rate. This is technically possible, but again, the requirements are absurdly specific. The jets need to be evenly spaced, which would require the comet's surface composition to be uniform at a level we've never observed in any natural comet. They need to fire with equal strength, which means the subsurface ice needs to be at the same temperature and pressure in 4 separate locations, and they need to stay active at exactly these locations as the comet moves through different regions of the solar system, experiencing different amounts of sunlight and heating. The odds of all these conditions being met by chance are, to put it mildly, not good. Then there's the reflective lobes hypothesis, which tries to explain the brightness variations without relying on shape alone. Maybe the comet's surface has regions that are significantly more reflective than others. Perhaps there are patches of clean water ice, or deposits of some mineral that catches sunlight and bounces it back toward Earth. If these reflective regions are positioned opposite each other on the nucleus, we'd see a brightness peak each time one of them rotates into view. 2 peaks per rotation. The math works. But once again, we run into the problem of maintenance. Comet surfaces aren't static. They're constantly being modified by sublimation, by dust deposition, by micrometeorite impacts. reflective patches should get covered with dust over time, especially as the comet approaches the Sun and outgassing ramps up. We should see the brightness variations fade or shift as the surface changes. We don't. The 2-hour pulse persists with the same amplitude, the same timing, mission after mission, observation after observation. Some researchers have proposed that maybe the comet's dust coma, the cloud of particles surrounding the nucleus, is creating the brightness variations. Perhaps dust is being ejected in a periodic pattern, creating temporary clouds that reflect more light when they align with our line of sight. This would explain why the brightness pulse is so regular, even if the nucleus itself is irregular. The problem with this idea is that dust clouds disperse. They don't maintain sharp boundaries or precise timing. Once dust leaves the nucleus, it spreads out, carried by solar radiation pressure and the comet's own outgassing. Within hours or days, any periodic structure in the dust distribution should blur into a more uniform coma, and yet the brightness variations continue, sharp and clear, without any sign of the smoothing we'd expect from a dispersing dust cloud. There's also been discussion of the comet's polarimetric properties, the way it affects the polarization of sunlight that reflects off it. 3I-ATLAS shows deep negative polarization branches, meaning the reflected light is polarized in an unusual way that we don't see in typical comets. This suggests the surface or coma has unique optical properties, possibly related to the size distribution of dust grains or the presence of specific minerals. Some scientists have wondered if these optical anomalies could be connected to the brightness variations, if there's some property of the comet's material that naturally produces periodic light effects. But polarization anomalies alone don't create precise timing. They might explain why the comet looks strange when we analyse its light, but they don't explain why it pulses with clockwork regularity. For that, you still need a mechanism that maintains periodicity over time, something that resists the natural tendency toward chaos and decay. What all these natural models have in common is that they require a level of precision and stability that nature rarely achieves and never maintains. They're not impossible, just improbable to the point where you start wondering if you're missing something fundamental. It's like finding a river that flows in a perfectly straight line for 100 miles. Rivers don't do that. They meander, they flood, they carve new channels. Straight river makes you think someone dug a canal. And that's where the conversation starts to shift, where scientists begin to quietly, carefully, with all the appropriate caveats and disclaimers, consider the possibility that maybe we're not looking at a comet that happens to behave like an engineered object. Maybe we're looking at an engineered object that happens to look like a comet. Because if you wanted to send a probe into another star system, if you wanted it to survive the journey and remain functional for thousands or millions of years, you'd design it to be robust, stable, self-regulating. You'd give it a spin for stability. You'd make it reflect light in a pattern that could be detected by anyone watching carefully. You'd make it look, from a distance, like it belongs, like it's natural, and then you'd send it on its way, knowing that if anyone noticed, they'd spend years trying to explain it with ice and rock and physics before they even considered the alternative. Part 5. The Threshold of Intent, the Engineered Lens. We've reached the point in this story where we need to talk about something that makes most scientists uncomfortable: intent, purpose, design. These are words that don't appear often in astrophysics journals because they imply agency, and agency implies intelligence, and intelligence from beyond Earth is a topic that sits at the edge of respectability in the scientific community. But the data from 3I-ATLAS is pushing us toward that edge, forcing us to at least consider what it would mean if this object were engineered. So let's put on that lens for a moment. Let's look at the evidence not as confused astronomers trying to explain away anomalies, but as engineers trying to understand a piece of technology. What would we see? First, we'd see stabilization. The 4-hour rotation period is remarkably stable, showing no signs of the decay or variation we'd expect from a natural object. In spacecraft design, this kind of stability is achieved through active control systems, reaction wheels, gyroscopes, thrusters that fire periodically to correct for drift. But you don't need complex electronics to achieve spin stability. You can do it mechanically, with a well-balanced rotor and maybe some internal masses that shift to compensate for external torques. It's the same principle that keeps a bicycle wheel stable when it's spinning. The faster it spins, the more it resists changes to its orientation. If 3I-ATLAS has some kind of internal mechanism, even something as simple as a dense core that's been deliberately balanced. It could maintain its rotation for centuries without active intervention. Second, we'd see the brightness variations as a signal. 2-hour pulses, regular as a heartbeat, visible from interstellar distances if you have the right instruments and you're watching carefully. This is exactly what you'd design if you wanted to mark an object as artificial, without being too obvious about it. You wouldn't broadcast radio signals because those are unmistakably technological. You'd use light, something that comets naturally produce, but you'd add a pattern, a rhythm that's just regular enough to make observers wonder. It's a whisper instead of a shout, a signal that says maybe I'm natural, maybe I'm not, but either way I'm worth watching. The 2-to-1 harmonic relationship between the rotation period and the brightness pulses is particularly suggestive. Harmonics don't happen by accident in engineering. They're designed. A lighthouse rotates at one speed, but its light flashes twice per rotation if it has 2 lamps positioned opposite each other. A satellite might spin for stability, but its solar panels or antennas create brightness variations at a different frequency depending on their configuration. If you were designing a probe that needed to be recognized as potentially artificial without screaming its presence, a harmonic relationship is exactly the kind of subtle clue you'd embed in its behavior. It's sophisticated enough that random chance becomes an uncomfortable explanation, but ambiguous enough that skeptics can still argue for natural causes. Then there's the question of why anyone would build such a thing. If 3I-ATLAS is a probe, what's its purpose? The most obvious answer is observation. You send probes to watch, to collect data, to learn about star systems you can't visit yourself. If you're a civilization with the technology to send objects on interstellar journeys, you'd want to know what's out there. Are there planets? Are they habitable? Are there other civilizations? A probe that looks like a comet is perfect camouflage. It moves through the solar system on a natural-looking trajectory, gets close to planets without raising alarms, and by the time anyone notices it's behaving strangely, it's already seen everything it came to see. Or maybe it's not about observation. Maybe it's a message, a deliberate marker left for anyone advanced enough to notice the patterns. The brightness pulses could be encoding information, a binary signal hidden in the timing variations that we haven't decoded yet. Or maybe the message is simpler. We were here, we passed through, we're watching. The very existence of an object that hovers at the boundary between natural and artificial is itself a message, a way of saying there's more out there than you thought, and maybe it's time to look harder. Of course, there's also the possibility that it's a relic, something that's been coasting through space for so long that its creators are gone, but the machine keeps running because that's what machines do. Stabilization systems don't require consciousness. Once you set something spinning with the right balance, it can maintain that spin for millions of years. The brightness variations could be powered by something as simple as reflective surfaces catching starlight, no batteries or reactors required. It's the ultimate long-term mission. Send a probe out into the galaxy, give it the simplest possible design that will survive indefinitely, and wait for someone to notice. But here's where the engineered lens gets uncomfortable. If 3I-ATLAS is artificial, it means we're not alone, and it means someone else has technology capable of interstellar travel. It means they've been watching us, or at least passing through our neighbourhood, and they've done it so subtly that we almost missed it. That realization comes with questions that don't have easy answers. Who are they? Where did they come from? Are there more probes like this one scattered throughout the galaxy, drifting from system to system, collecting data or delivering messages to anyone capable of understanding them? And it forces us to ask why we're only noticing now. How many other objects have passed through our solar system exhibiting similar patterns, and we dismissed them as natural because we weren't looking carefully enough? Oumuamua accelerated in a way that couldn't be explained by outgassing alone, but most scientists eventually settled on exotic theories about hydrogen icebergs or nitrogen sheets rather than consider artificial explanations. Are we so committed to natural causes that we're willing to invent increasingly improbable mechanisms just to avoid saying the word that changes everything? The truth is, we don't have enough data to say definitively that 3I-ATLAS is engineered. We have patterns that are hard to explain naturally, and we have behaviours that would make sense if the object were designed, but that's not proof. It's not even strong evidence by the rigorous standards of science. It's a hypothesis, one among several, and it happens to be the hypothesis that most scientists would prefer to avoid unless every other option has been exhausted. But exhaustion is coming. With every observation that confirms the periodicity, with every model that fails to explain the stability, we're running out of natural explanations that don't require us to invoke coincidences so unlikely they might as well be miracles. And at some point, when the improbable becomes impossible, we have to start taking the uncomfortable alternative seriously. We have to start asking not whether 3I-ATLAS could be engineered, but what it means if it is. And that question, that shift from could to is the threshold we're approaching now, whether we're ready for it or not. Part 6. The strange chemistry of 3I-ATLAS. Let's talk about what this comet is made of, because the chemistry is just as strange as the behaviour. When the James Webb Space Telescope turned its infrared instruments toward 3I-ATLAS, it found something unexpected. The comet's coma is dominated by carbon dioxide. Not water vapour, which is the primary component of most comets we've studied, but CO2 in concentrations that are unusually high for an object this far from the Sun. Carbon dioxide sublimates at lower temperatures than water ice, which means it starts outgassing when the comet is still far from the solar system's inner regions. This isn't unheard of, but it's not common either. Most comets are water-rich because water ice is abundant in the regions where comets form, and it's stable at the low temperatures found in the outer solar system and interstellar space. Carbon dioxide is more volatile, more likely to sublimate away during close passes to a star or during the comet's long journey through space. The fact that 3I-ATLAS still has so much of it suggests either it formed in an unusually cold, CO2-rich environment, or it's been protected somehow from the processes that would normally deplete its volatile inventory. Then there's the water emission, detected by the SWIFT spacecraft's ultraviolet instruments. SWIFT caught 3I-ATLAS emitting water vapour when it was still quite far from the Sun, farther out than most comets begin their water activity. This is puzzling because water ice requires significant solar heating to sublimate. You need temperatures above about 200 Kelvin, which typically doesn't happen until a comet gets inside of Jupiter's orbit. But 3I-ATLAS was active earlier, suggesting either its surface is darker than typical comets, absorbing more heat, or something internal is driving the outgassing beyond just solar radiation. The polarimetry data adds another layer of strangeness. When light reflects off a comet's dust particles, it becomes polarized in predictable ways based on the size, shape, and composition of those particles. Most comets show a characteristic polarization curve, low polarization at small phase angles, rising to a peak, then declining. 3I-ATLAS shows deep negative polarization branches, meaning at certain angles the reflected light is polarized in the opposite direction from what we'd expect. This signature is rare, seen in only a handful of comets, and it suggests the dust grains are either unusually large, unusually shaped, or made of materials with optical properties we don't fully understand. Spectroscopy from ground-based telescopes has detected cyanide and nickel emission lines in the comet's coma. Cyanide, in the form of CN radicals, is common in comets. It comes from the breakdown of more complex organic molecules as they are exposed to sunlight. But the strength of the cyanide signal in 3I-ATLAS is notable, suggesting a higher than typical abundance of organic compounds in its nucleus. Nickel, on the other hand, is unusual. Metal atoms don't typically show up strongly in comet spectra, because metals don't sublimate easily. You need temperatures high enough to vaporize solid metal, or you need some process that's releasing metal atoms into the coma beyond simple sublimation. The presence of nickel has sparked particular interest, because it might indicate the comet contains metallic grains or minerals that are being released as the surface erodes. Some researchers have suggested that interstellar comets might incorporate materials from their journey through the galaxy, picking up dust grains from the interstellar medium or from supernova ejecta that crossed their path. If 3I-ATLAS passed through regions enriched in heavy elements, it might have accumulated a coating or embedded particles of metals that now show up in its outgassing. That's a natural explanation, but it requires the comet to have had specific encounters during its millions or billions of years wandering between stars. Or, and this is where the chemistry starts to feel less natural, the nickel could be structural. If you were building a probe designed to look like a comet, you'd need materials that could survive the journey. Metals, particularly nickel-iron alloys, are excellent for long-term structural integrity. They don't degrade in vacuum. They can withstand cosmic ray bombardment, and they're stable across enormous temperature ranges. A metal core or framework covered with ice would appear comet-like from a distance, And as the ice sublimates away during solar approach, you might start seeing spectroscopic signatures of the underlying structure. It's speculative, but it's not impossible. The carbon dioxide dominance is particularly interesting when you think about probe design. CO2 is a good working fluid for certain types of propulsion or thermal management systems. It's easy to store, it sublimates predictably when heated, and it can create thrust if vented through nozzles. If you wanted to make small adjustments to a probe's trajectory using materials that would blend in with natural comet outgassing, carbon dioxide would be a smart choice. From a distance, observers would just see a CO2-rich comet and assume it formed in a cold environment. They wouldn't think maneuvering jets. The water emission at large distances could also serve a dual purpose. Water vapour creates a coma, a visible cloud around the nucleus that makes the object easier to detect and track. If you're a probe that wants to be found eventually but not too obviously, you'd turn on your water outgassing at distances where it's unusual but not impossible. You'd create a signature that makes amateur and professional astronomers point their telescopes your way, giving you maximum observation time as you pass through the system. It's counterintuitive, but sometimes the best camouflage isn't invisibility. It's being exactly strange enough to be interesting, but not so strange that you trigger immediate alarm. The polarimetry anomalies could indicate surface features that aren't natural. Dust grains from comets are typically irregular, fragments of larger particles broken down by sublimation and thermal stress. They create polarization signatures that have been well studied and modelled, but engineered surfaces, panels, mirrors, even textured coatings designed to manage heat or light would create different optical effects. They might produce polarization curves that don't match natural dust, especially if those surfaces are made of materials not commonly found in comets. We don't have enough data yet to say this is what's happening with 3I-ATLAS, but the deep negative polarization branches are waving a red flag, suggesting something about its light-scattering properties doesn't fit the standard comet template. There's also the question of what the chemistry tells us about where this object came from. Interstellar space is not uniform. Different regions of the galaxy have different compositions based on their history of star formation and supernova enrichment. A comet that formed in a system rich in carbon dioxide might come from a region where CO2 ice is more abundant than water ice, perhaps near the atmosphere of a failed star or brown dwarf where carbon chemistry dominates. The presence of organic compounds and metals might indicate formation near a dying star that was throwing off heavy elements into space. These are all natural scenarios, but they require very specific conditions that we don't see in our own solar system's comet-forming regions. Or maybe the chemistry is telling us that 3I-ATLAS isn't a product of planetary formation at all. Maybe it's a collection of materials chosen for specific purposes, assembled rather than accreted, designed to survive and function across interstellar distances. The CO2 for propulsion or thermal control, the water for visibility and coma creation, the organics for radiation shielding or structural binding, the metals for framework and longevity, each component serving a role in a system that needs to operate for geological timescales without maintenance. What really bothers some chemists and planetary scientists isn't that 3I-ATLAS has unusual abundances. Unusual happens. Nature is diverse and surprising. What bothers them is that the unusual abundances align so well with what you'd expect from something designed. It's like finding a rock with high iron content, high carbon content, and traces of chromium and nickel, and realizing those are exactly the ingredients you'd need to make stainless steel. Natural? Sure, it's possible. But when you find that rock shaped like a knife with a sharp edge and a handle, you stop thinking geology and start thinking archaeology. 3I-ATLAS's chemistry is our knife-shaped rock. Each individual element in its composition has a natural explanation. But all of them together, combined with the behavioral anomalies, the precise rotation, the harmonic brightness variations, create a picture that's hard to reconcile with random chance. It's a composition that makes sense if you're trying to build something that will last forever, operate autonomously, and blend in with the natural objects around it until someone looks closely enough to realize something's different. And that should make you wonder what else we've missed. How many other interstellar visitors have passed through with strange chemistries and regular patterns, and we catalogued them as comets because we weren't looking for anything else? How many times have we explained away the knife because we were so certain we were looking at geology? Because if 3I-ATLAS is the first time we've noticed, it probably isn't the first time it's happened. It's just the first time we were paying attention. Part 7, dust, spectra, and morphology. The coma's hidden story. When you observe a comet, you're not just seeing a frozen chunk of ice and rock. You're seeing a dynamic system, a cloud of gas and dust that surrounds the nucleus and extends for thousands or millions of kilometers into space. This coma, as astronomers call it, is where much of the interesting physics happens, and it's where 3I-ATLAS continues to defy easy explanation. Ground-based spectroscopy campaigns have been monitoring the comet since its discovery, tracking how its spectrum changes as it moves closer to the Sun. Spectra are like fingerprints for chemical composition. Different molecules absorb and emit light at specific wavelengths, and by splitting a comet's light into its component colours, we can identify what gases are present in the coma. For 3I-ATLAS, the spectra show the expected lines from cyanide, carbon dioxide, and water vapour that we already discussed. But there are also features that don't match standard comet models perfectly. Weak lines that might indicate trace molecules we haven't identified yet, or absorption features that suggest dust with unusual properties. The dust itself is a major focus of study. When ice sublimates from a comet's surface, it carries dust particles along with it, lifted by the expanding gas and pushed outward by solar radiation pressure. These particles scatter sunlight, which is how we see the coma and tail. By analysing how the brightness of the coma changes with distance from the nucleus, astronomers can estimate the size distribution and production rate of the dust. For 3I-ATLAS, the dust production seems lower than expected for a comet of its brightness. It's producing plenty of gas, but not as much dust, which suggests either its nucleus has less dust mixed into the ice, or the dust particles are larger and heavier, harder to lift off the surface. Large dust particles are interesting because they don't disperse as quickly. They create a more compact, denser coma that stays closer to the nucleus. This could explain some of the brightness variations. If the comet is ejecting dust in specific directions or at specific times during its rotation, you might see brightness pulses as these dust clouds move in and out of our line of sight. But again, this requires a level of control over the dust ejection process that's hard to achieve naturally. You'd need jets that turn on and off with precise timing, always firing at the same point in the rotation, cycle, always producing the same amount of dust. That's not how comets typically behave. The tail evolution is another piece of the puzzle. Comets develop tails as solar wind and radiation pressure push gas and dust away from the Sun. The gas forms an ion tail that points directly away from the Sun, while the dust forms a curved tail that lags behind the comet's orbit. 3I-ATLAS has both types of tails, which is normal. What's less normal is how stable they appear. Most active comets show variability in their tails, with disconnection events where the ion tail breaks off and reforms, or dust clouds that create streamers and knots in the dust tail. 3I-ATLAS's tails are remarkably smooth and consistent, without the dramatic structures you'd expect from a comet with variable outgassing. Colour measurements add another dimension to the analysis. Comets can appear reddish, bluish, or neutral in colour depending on their dust composition and the relative amounts of gas and dust in the coma. 3I-ATLAS shows colour variations that correlate with its brightness changes, getting slightly bluer when it brightens and redder when it dims. This could indicate that the material being released during bright phases has different properties than the material released during dim phases, possibly because different regions of the surface become active as the comet rotates. Or it could mean that reflective surfaces are dominating the light during bright phases, contributing bluer, sunlight-coloured light, while the dusty coma contributes redder light during dim phases. Polarimetry observations, which we touched on earlier, have been conducted by multiple teams using various telescopes. The deep negative polarization branches show up consistently across different wavelengths and viewing geometries, which means they're a real property of the comet, not an artifact of how we're observing it. Some researchers have suggested that the dust grains might be coated with organic materials that create unusual optical effects, or that the grains are fractals with complex surface structures. Others have proposed that the coma might contain a population of very large particles, essentially pebbles rather than dust, that scatter light differently than typical comet dust. But there's another possibility that's been quietly mentioned in some of the more speculative papers. If the comet has structured surfaces, panels or facets that reflect light coherently, you'd expect polarization anomalies. Mirrors produce highly polarized reflections. Metallic surfaces can create polarization patterns that don't match irregular dust. The fact that 3I-ATLAS shows these anomalies in combination with its other unusual features, makes you wonder if what we're calling dust might not be entirely dust. Maybe we're seeing light scattered from surfaces that were designed to scatter light in specific ways, mixed in with natural comet dust to create an overall appearance that's mostly comet-like, but not quite. The morphology of the coma, its overall shape and structure, has been analysed using high-resolution imaging from large ground-based telescopes. Most comets show jets or fans, bright streaks in the coma that indicate where active regions on the nucleus are ejecting material. 3I-ATLAS shows a more uniform coma, without the dramatic jet structures you'd expect from a rapidly rotating, asymmetrically outgassing nucleus. It's as if the outgassing is happening evenly all over the surface, or at least evenly enough that individual jets don't dominate the appearance. This fits with the idea of balanced activity, but it's another anomaly that stacks on top of all the others. There have also been attempts to model the dust dynamics, to simulate how particles leave the nucleus and move through the coma based on gas drag, radiation pressure, and the comet's rotation. These models generally succeed at reproducing the overall appearance of the coma, but they struggle with the fine details. The brightness variations, the colour changes, the polarisation anomalies, none of these fit perfectly into the models unless you add special conditions. You need to assume specific dust properties, specific gas production rates, specific surface features, and even then the fit isn't great. It's like trying to assemble a jigsaw puzzle where most of the pieces fit but a few don't quite match, and you're not sure if it's because you're missing pieces or because someone mixed in pieces from a different puzzle. The spectroscopic monitoring has also revealed temporal variations. Some emission lines get stronger and weaker, with a periodicity that matches the rotation. This is expected if different regions of the surface have different compositions and become visible as the comet spins. But the phase relationship between different molecules is unusual. Water vapour peaks at a slightly different point in the rotation cycle than cyanide, which peaks at a different point than carbon dioxide. In a natural comet, you'd expect these variations to be somewhat correlated because they're all driven by solar heating of the surface. The fact that they're offset suggests either very specific compositional variations across the surface or multiple processes operating independently. What all of this morphological and spectroscopic data tells us is that 3I-ATLAS is consistent in its inconsistency. Every time we look at it in a new way, with a new instrument or technique, we find something that's slightly off from what comets normally do. Not wildly different, not obviously artificial, just consistently unusual in ways that are hard to explain with a single natural model. It's death by 1,000 cuts for the hypothesis that this is just a comet. Each individual cut is small, explainable, maybe even expected given the diversity of comets in the universe. But when you add them all up, when you step back and look at the full picture, the accumulation of anomalies starts to look less like bad luck and more like a pattern. And patterns, especially patterns that repeat with mathematical precision, tend to have causes. The question is whether the cause is billions of years of random chance sculpting the perfect comet, or whether someone sculpted it on purpose and sent it our way knowing we'd eventually notice that something didn't quite fit. Part 8. SETI Strikes Back. The Alien Debate Reopened. The search for extraterrestrial intelligence has always operated at the fringes of respectable astronomy. Tolerated but not embraced, funded sparingly, regarded with skepticism by the mainstream. But 3I-ATLAS has dragged SETI back into the conversation, whether the scientist involved wanted it or not. And leading that charge, as he often does, is Avi Loeb, the Harvard astrophysicist who's made a career out of asking uncomfortable questions about interstellar objects. Loeb has been vocal about 3I-ATLAS since its discovery, suggesting in interviews and preprints that its behaviour warrants serious consideration of the artificial hypothesis. He points to the precise rotation, the brightness variations, the chemical anomalies, all the things we've discussed, and argues that dismissing the possibility of extraterrestrial technology is itself unscientific. Science, he says, should follow the evidence wherever it leads, even if that destination makes us uncomfortable. And the evidence here, he argues, is consistent with an object designed to be noticed by anyone paying attention. He's drawn comparisons to Oumuamua, the interstellar visitor he famously suggested might be a light sail, a thin reflective structure pushed by starlight, or perhaps even by lasers from its point of origin. That hypothesis was met with significant pushback from the astronomical community, with many researchers publishing papers explaining Oumuamua's acceleration through natural mechanisms like hydrogen outgassing or exotic ice compositions. But Loeb has stood by his assessment, pointing out that the natural explanations require their own set of unlikely assumptions, and that we shouldn't apply different standards of evidence to artificial versus natural hypotheses. With 3I-ATLAS, he's being more cautious, more methodical, but the underlying argument is the same. We have an object exhibiting behaviour that's hard to explain naturally. Instead of inventing increasingly complicated natural models, we should at least investigate the possibility that the simple explanation that it's artificial might be correct. He's called for radio telescope observations to search for signals, for infrared surveys to look for excess heat that might indicate power generation, for detailed spectroscopy to search for industrial pollutants, or unusual isotope ratios that wouldn't occur in natural objects. The SETI community's response has been mixed. Some researchers have embraced the opportunity to turn their instruments toward 3I-ATLAS, conducting searches for radio emissions at various frequencies. So far, they've found nothing. No obvious signals, no regular pulses in the radio spectrum that would indicate intentional transmission. But as Loeb and others have pointed out, silence doesn't mean absence. A probe designed for long-term operation might not broadcast continuously. It might be dormant, conserving power, or it might communicate in ways we're not looking for, using optical lasers or neutrino beams or modulation techniques we haven't considered. Other SETI researchers have been more sceptical, publishing papers arguing against the artificial interpretation. They point out that the lack of non-gravitational acceleration, unlike Oumuamua, suggests 3I-ATLAS is moving purely under gravitational influence, which is what you'd expect from a natural comet. They note that the brightness variations could be explained by shape and rotation without invoking reflective panels or structured surfaces. They emphasize that extraordinary claims require extraordinary evidence, and periodic light curves aren't extraordinary enough. This is where the debate gets philosophical. What constitutes extraordinary evidence? If we demand absolute proof before considering artificial explanations, we'll never seriously investigate objects like 3I-ATLAS until it's too late, until they've passed through the solar system and disappeared back into interstellar space. But if we're too quick to jump to artificial conclusions, we risk becoming the scientists who cried alien, losing credibility and wasting resources on wild goose chases. It's a balance, and different researchers land at different points on that spectrum. The public, predictably, has been more willing to entertain exotic possibilities. 3I-ATLAS has generated significant media attention, spawning articles, documentaries, and endless speculation on social media. For many people, the idea that we might be observing alien technology is exciting, even thrilling, a sign that we're not alone in the universe and that contact might be closer than we thought. For others, it's unsettling, raising questions about who they are and what they want, and whether a probe observing our solar system might be the precursor to something more direct. What's interesting about this particular debate is how it's evolved compared to the Oumuamua controversy. Back in 2017 and 2018, when Loeb first suggested Oumuamua might be artificial, the response from the astronomical community was swift and largely negative. Papers were published debunking the hypothesis, interviews were given emphasizing natural explanations, and there was a sense that Loeb had gone too far, crossed a line from respectable speculation into sensationalism. But with 3I-ATLAS, the response has been more measured. Scientists are still emphasizing natural explanations, but there's less of the reflexive dismissal, more willingness to say we don't know yet, let's keep watching. Part of this shift might be because 3I-ATLAS's anomalies are more numerous and harder to explain away individually. Part of it might be because the astronomical community has had time to grapple with the implications of interstellar objects and the questions they raise. And part of it might be because, quietly, some scientists are starting to wonder if maybe Loeb has a point, if maybe we've been too quick to dismiss artificial hypotheses in the past because of social and professional pressures rather than scientific reasoning. There have been other interesting developments in the broader SETI field that give context to this debate. In 2025, there have been several false alarms, candidate signals that looked promising initially, but turned out to be instrumental artifacts or terrestrial interference. Each false alarm reinforces the need for caution and thorough verification before announcing discoveries. But they also show that the field is active, that people are looking, and that our detection capabilities are improving. We're scanning more of the sky at more frequencies, with better sensitivity than ever before. If there are artificial signals out there, we're more likely to find them now than at any point in history. And that brings us back to 3I-ATLAS, and the question of why, if it's artificial, it's not broadcasting, obviously. One possibility is that it's not meant for us. It might be a probe on a mission that has nothing to do with Earth, passing through our system en route to somewhere else. And we just happen to be noticing it because we've gotten good enough at astronomy to spot the anomalies. Another possibility is that it is meant for us, but the message is subtle, encoded in the behaviour rather than in radio signals, designed to be discovered only by civilizations that have reached a certain level of technological sophistication. You wouldn't advertise to a species that can't detect you. You'd wait until they notice you on their own, and then maybe, once they're paying attention, you'd reveal more. Or maybe there is no message. Maybe 3I-ATLAS is exactly what it appears to be, a comet with unusual but natural properties that will eventually explain once we have better data. Maybe in 5 or 10 years, we'll look back on this debate and laugh at how quickly we jumped to alien conclusions, how we let our desire for contact cloud our scientific judgment. That's possible. It's even likely, if you go by historical precedent. Most anomalies turn out to be natural once we understand them better, but maybe, just maybe, this is the time when the anomaly doesn't resolve into something natural. Maybe this is the moment when we finally find what SETI has been searching for all these decades. Not a radio signal from across the galaxy, but a visitor, silent and patient, spinning through our solar system with a precision that speaks louder than any broadcast. And if that's the case, if 3I-ATLAS really is artificial, then the debate we're having now about evidence standards and scientific caution and professional reputations will seem quaint in retrospect. Because once we know we're not alone, once we have proof that intelligence exists beyond Earth, everything changes. The question is whether we're ready for that change, whether we're willing to seriously consider it as a possibility, or whether we'll keep inventing natural explanations until the evidence becomes so overwhelming that denial is no longer an option. Part 9. The Skeptic's Case. Could it all be a data illusion? Let's pump the brakes for a moment and consider the possibility that we're seeing patterns where none exist. Science has a long history of false positives, of signals that looked compelling until someone realised they were artefacts of measurement or analysis. The face on Mars turned out to be a hill lit from an unusual angle. Pulsars were briefly considered alien beacons until we understood them as rotating neutron stars. Cold fusion promised unlimited energy until careful replication failed to reproduce the results. So before we get too excited about 3I-ATLAS and its precise periodicity, we need to seriously evaluate whether the patterns we're seeing might be illusions, created by how we're collecting and analysing the data. The first concern is sampling bias. When you observe a comet, you don't watch it continuously. You take images when the telescope is available, when weather permits, when the comet is above the horizon, and positioned away from the sun and moon. These observations are scattered irregularly across time, with gaps that can be hours or days long depending on circumstances. When you try to detect periodicity in data with irregular sampling, you can get false positives, apparent cycles that are actually artifacts of when you happen to look. This is where the choice of the Lomskagel periodogram becomes important. It's specifically designed to handle irregular sampling, unlike traditional Fourier analysis which assumes evenly spaced data points. But even Lomskagel has limitations. If your observation cadence happens to resonate with a real period, you'll detect it strongly. But if your cadence creates aliasing, where you're essentially undersampling the signal, you might detect periods that are harmonics or subharmonics of the true period, or you might detect false periods that don't exist at all. It's the stroboscopic effect, like watching a wagon wheel on film that appears to rotate backward because the frame rate interacts with the wheel's spin rate in misleading ways. Medvedev and Pavlov were aware of this risk, which is why they quoted error margins on their period estimates. The 4-hour positional shift has a 2-hour uncertainty, meaning the true period could be anywhere from 2 to 6 hours. The 2-hour brightness pulse has a 1.33-hour uncertainty, so it could be as short as 0.67 hours or as long as 3.33 hours. These are large uncertainties, and they overlap in ways that make you wonder whether the 2-to-1 harmonic relationship is as clean as it initially appears. Maybe we're seeing two independent periods that happen to be roughly related, and our pattern-seeking brains are imposing a harmonic structure that isn't really there. There's also the question of statistical significance. When you search for periodicities in noisy data, you're essentially conducting multiple statistical tests, one for each possible period you're checking. The more tests you run, the higher the probability that one of them will show a significant result purely by chance. This is the multiple comparisons problem, and it's a notorious source of false positives in astronomy and other fields. If you look at enough comets for enough different periods, eventually you'll find one that shows apparent periodicity just from random fluctuations in the data. The standard way to address this is to calculate a false alarm probability, an estimate of how likely you'd be to see a signal this strong if there were no real periodicity present. Medvedev and Pavlov's telegram doesn't include detailed false alarm calculations, which is understandable for a preliminary announcement, but it means we don't have a quantitative assessment of how confident we should be in their results. Until other teams independently confirm the periodicity using different datasets and analysis methods, there's room for healthy skepticism about whether the signal is real. Cadence effects are another potential source of illusion. If multiple observatories are tracking 3I-ATLAS, and they're all scheduling observations based on similar constraints like the comet's visibility and telescope availability, you might end up with a dataset that has hidden structure in its sampling pattern. For example, if observations tend to cluster around certain times of day because that's when the comet is highest in the sky from most observatories, and those times happen to align with a particular rotation phase of the comet, you might preferentially sample bright phases and miss dim phases, creating an apparent brightness variation that's really just a selection effect. Aliasing, which I mentioned earlier, is particularly insidious because it can create strong false signals that look just as convincing as real periodicities. If the true rotation period of 3I-ATLAS is, say, 3 hours, but observations happen to be spaced roughly 6 hours apart, you might detect a 6-hour period instead, or a 1.5-hour period, or any number of aliases depending on the exact sampling pattern. The Lomsgagel periodogram can help identify aliases, but it's not foolproof, especially when the data is sparse or noisy. There's also the possibility that what we're seeing is a beat frequency, an interference pattern between two real but unrelated periodicities. Imagine the comet has an irregular rotation with a roughly 4-hour average period, but it's also precessing or wobbling with a different period. The combination of these two motions could create brightness variations at yet another period, and depending on how they interact, you might see patterns that look regular, even though the underlying motions are chaotic. Disentangling beat frequencies from data requires long observation baselines and careful modelling, neither of which we have yet for 3I-ATLAS. Then there's the human element. Scientists, like everyone else, have expectations and biases. When you're analysing data looking for patterns, there's a risk that you'll find what you're looking for even if it's not really there, because your analysis choices, the periods you test, the significance thresholds you set, the outliers you exclude, all of these can subtly bias the results toward confirming your hypothesis. This isn't fraud or misconduct, it's just human psychology, and it's why replication and peer review are so important. Results need to be independently verified by researchers who don't have the same investment in a particular outcome. In the case of 3I-ATLAS, we're still in the early stages of that verification process. Medvedev and Pavlov published their findings, but we haven't yet seen detailed follow-up studies from other teams confirming or refuting the periodicity. Maybe those studies are in progress, data being analysed, papers being written, or maybe other teams are seeing different results, less clear patterns, and they're holding back until they understand the discrepancy. In science, negative results often go unpublished, which means we might not hear about failed replication attempts until much later, if at all. There are also alternative explanations for regular behaviour that don't require perfect symmetry or artificial engineering. For instance, tidal forces during close approaches to other stars during the comet's interstellar journey might have spun it up and damped out wobbles, leaving it in a relatively stable rotation state. This is called tidal locking in the extreme case, though what we'd be seeing with 3I-ATLAS is more like tidal stabilisation. It's not impossible, but it requires specific encounter scenarios that we can't verify without knowing the comet's full trajectory through the galaxy. Or consider that the outgassing itself might create feedback loops that stabilise the rotation. If jets preferentially fire when certain regions of the surface reach specific temperatures, and those jets happen to be positioned such that their torques cancel out, you could get self-regulating behaviour that maintains a constant spin rate. This is a type of dynamical equilibrium, and while it seems unlikely, Nature has surprised us before with self-organizing systems that appear designed but aren't. The point. Raising all these skeptical possibilities isn't to dismiss the findings about 3I-ATLAS, but to emphasize that extraordinary claims really do require extraordinary evidence, and we're not there yet. We have intriguing data, suggestive patterns, but we don't have the kind of ironclad, independently replicated, alternative, hypotheses-excluded proof that would justify confidently declaring this comet is behaving in fundamentally unnatural ways. Maybe we'll get there as more observations come in and more analysis is done. Or maybe the pattern will fade, the periodicity will turn out to be less robust than it initially appeared, and 3I-ATLAS will become a cautionary tale about jumping to conclusions from preliminary data. But here's the thing that should keep both believers and skeptics humble. We're watching this unfold in real time. Unlike Oumuamua, which was discovered on its way out and disappeared before we could mount a serious observational campaign, 3I-ATLAS is still here, still accessible to our telescopes, still available for study. If the periodicity is real, it should persist in new data. If it's an illusion, it should fall apart under scrutiny. The truth, whatever it is, will emerge from the steady accumulation of observations and the careful, unglamorous work of data analysis. That's how science works. Not through dramatic announcements and wild speculation, but through patient investigation and rigorous verification. So while we wait for that process to unfold, it's worth remembering that the most important words in science are often not, "We've discovered something amazing," but "We need more data." Part 10. Reverse engineering the rhythm, if it were engineered. Let's engage in a thought experiment. Forget for a moment about what 3I-ATLAS probably is, and instead ask what it would need to be if it were engineered. If you were an advanced civilization capable of sending probes on interstellar journeys, and you wanted to create something that could traverse the galaxy, survive for millions of years, and still accomplish its mission when it finally encountered a star system, what would you build? And more importantly, would it look anything like what we're observing? Start with the basic requirements. Your probe needs to survive the interstellar medium, which sounds empty but isn't quite. There's gas out there, thin but present, perhaps 1 atom per cubic centimetre on average, more in some regions, less in others, at interstellar velocities tens of kilometres per second or more. Even individual atoms become micrometeorites, sandblasting your probe's surface over millennia. So you'd want shielding, perhaps ice serving double duty as both protective coating and propellant reserve. A comet disguise isn't just camouflage, it's practical engineering. The 4-hour rotation period makes sense from a stability perspective. Spin stabilization is one of the oldest tricks in aerospace engineering used by everything from rifle bullets to spacecraft. A spinning object resists changes to its orientation, maintaining its axis direction through angular momentum conservation. For a probe that needs to operate autonomously for geological timescales, passive stability systems are preferable to active ones because they don't require power or control systems that might fail. Set it spinning during launch, give it a moment of inertia distribution that resists tumbling, and it'll maintain that spin essentially forever in the vacuum of space. 4 hours is slow enough that centrifugal forces aren't problematic for structural integrity, but fast enough that you get good stability. It's also a period that's easy to measure precisely from a distance. Not so fast that you need high-speed cameras, not so slow that you need days of observation to characterize it. If you're trying to create a signal that says "pay attention to me," a multi-hour period is in the sweet spot of detectability. The 2-hour brightness pulses could be achieved with remarkable simplicity. 2 reflective surfaces, positioned opposite each other on the rotating probe, catching sunlight and directing it outward. No electronics required, no moving parts beyond the rotation itself. It's a passive optical signal generator, the interstellar equivalent of a lighthouse, except instead of warning ships away from rocks, it's drawing attention from anyone watching the sky carefully enough. The 2-to-1 harmonic with the rotation period is elegant mathematics, the kind of ratio that doesn't scream artificial, but certainly whispers it to anyone doing the analysis. But why make it detectable at all? Why not build a stealth probe? There are a few possibilities. One is that detection is the goal. You're conducting a survey of the galaxy, cataloguing which star systems have civilizations advanced enough to notice you. When a civilization detects your probe and recognizes it as artificial, that's your data point. You've identified a species that's reached a certain technological threshold. Maybe you send that information back home through some mechanism we can't detect. Maybe the probe itself stores the observation and will report it when it eventually returns to its origin, assuming it's on some vast loop through the galaxy. Another possibility is that the probe is meant to be an invitation. You want to be detected because detection is the first step in contact, but you don't want to be too obvious because that might cause panic or trigger unpredictable responses. So you create something ambiguous, something that hovers at the boundary between natural and artificial, and you let the local civilization debate and study and eventually, maybe, reach the conclusion that they're not alone. It's a soft disclosure, gentler than parking a mothership in orbit and announcing your presence with radio broadcasts. Or maybe the probe is simply old, designed by a civilization that no longer exists or that's moved on to concerns we can't imagine. Its creators sent it out millions of years ago with instructions to visit star systems and observe and report, and it's still following those instructions even though no one may be listening anymore. The detectability isn't strategic, it's just a consequence of how it was built. Functional features that happen to create observable patterns. The two reflective surfaces might be solar panels, or radiators, or sensor arrays, serving practical purposes in the probe's operation while incidentally creating the brightness pulses we're tracking. But this also raises uncomfortable questions. If building such probes is relatively straightforward for a sufficiently advanced civilization, why aren't we seeing more of them? The galaxy is billions of years old. There's been plenty of time for multiple civilizations to arise, build probes, and send them out. We should be swimming in interstellar artifacts, not puzzling over one or two ambiguous objects every few years. This is a variation of the Fermi paradox. If they exist and they're exploring, where is everybody? Maybe we are seeing more of them, but we keep classifying them as natural objects because we're not looking for the right signatures. Maybe Oumuamua was one. Maybe others have passed through undetected or were noticed, but catalogued as ordinary asteroids or comets because no one ran the detailed analysis that would reveal the anomalies. Our astronomical surveys are getting better, our data analysis more sophisticated, and maybe we're finally reaching the point where we can distinguish the artificial from the natural if we're willing to seriously consider the possibility. Or maybe 3I-ATLAS isn't a probe at all. Maybe it's a ship, or a habitat, or a piece of debris from some catastrophic event we can't imagine. The options multiply once you accept that something might be artificial. It doesn't have to be a probe with sensors and mission objectives. It could be anything someone built, for any purpose, at any point in the galaxy's long history. Here's what keeps me awake thinking about this. If 3I-ATLAS is engineered, it means the engineering philosophy that created it is fundamentally different from ours. We build things to last decades, maybe centuries if we're ambitious. They built something to last millions of years, to cross the galaxy, to arrive at distant stars and still function. The gap between their capabilities and ours isn't just technological, it's conceptual. They think on timescales we can barely comprehend. They plan for contingencies we'd never consider. They value patience and longevity in ways that might be incomprehensible to a species that's barely left its home planet. And if that's true, if there really is someone out there operating at that level, then detecting 3I-ATLAS isn't just an astronomical discovery, it's a mirror showing us how small we are, how young, how much we have to learn. Because they figured out how to send messages across the galaxy using nothing but ice and math and precision, while we're still arguing about whether the patterns we're seeing are real. That's not a technology gap, that's a chasm. And standing at the edge of that chasm, looking across at what might be on the other side, is both thrilling and terrifying in ways that will keep you staring at the ceiling long after you should be asleep. Part 11. Mars Orbiter. Images. ESA's ExoMars and Mars Express witnessed 3I-ATLAS. On October 3rd, 2025, something remarkable happened. 3I-ATLAS passed within 12 million miles of Mars, close enough that spacecraft orbiting the red planet could turn their cameras toward it and capture images of an interstellar visitor passing through our cosmic neighbourhood. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express both trained their instruments on the comet, giving us some of the closest views we've had from anywhere beyond Earth. The images aren't glamorous. This isn't Hollywood, it's science, and science often deals in faint dots and grainy pixels. The ExoMars images show 3I-ATLAS as exactly that, a faint glowing dot surrounded by a diffuse coma. But even from these modest images, we can extract valuable information about the comet's brightness, the extent of its coma, and how it appears from a different vantage point than Earth-based observers have. What's particularly valuable about the Mars observations is the viewing geometry. From Earth, we see 3I-ATLAS from one angle, with the Sun illuminating it in specific ways based on its position relative to us. From Mars, the geometry is different. The comet is lit from a different angle, and spacecraft orbiting Mars see different faces of the coma, potentially revealing structures or features that aren't visible from Earth. It's like having two cameras pointed at an object from different directions. The combination gives you stereo vision, depth perception, information about three-dimensional structure that you can't get from a single viewpoint. The Mars Express observations included spectroscopic data, measurements of what wavelengths of light the comet is emitting or reflecting. This adds to the growing database of spectroscopic information from ground-based telescopes and space observatories, helping to constrain models of the comet's composition and activity. Every new dataset is another piece of the puzzle, another constraint that natural or artificial models have to satisfy. NASA's Perseverance rover also got in on the action, capturing images of the comet from the Martian surface. These images show 3I-ATLAS as a streaky figure, the streak likely caused by the comet's movement across the sky during the exposure time. It's a different perspective again, looking up from a planetary surface rather than down from orbit, and it demonstrates the coordination possible when multiple space agencies and instruments work together to observe a single target. But here's where politics and practicality collide with science. The US government shutdown that was ongoing at the time of the Mars Closest Approach has meant that additional data from NASA's Mars instruments remains unavailable or at least unpublished. Budget fights in Washington have real consequences for science, delaying data release, preventing follow-up observations, leaving researchers frustrated and incomplete datasets sitting in archives, waiting for someone to get the funding to analyze them. This isn't unique to 3I-ATLAS. It's a recurring problem in planetary science. Missions cost billions of dollars and take decades to plan and execute, but the data analysis and publication phase is often underfunded, understaffed, treated as less important than the exciting work of building and launching spacecraft. So you end up with situations like this, where we have valuable observations sitting on hard drives at NASA centers, and the scientists who could be analyzing them are furloughed, or working without pay, or simply don't have the resources to do the work properly. The European data has been more forthcoming, perhaps because ESA's funding structure is less susceptible to sudden political shifts. The images and spectra from ExoMars and Mars Express are being published, shared with the international community, feeding into the broader effort to understand what 3I-ATLAS is and how it behaves. This highlights both the importance of international collaboration in space science and the vulnerability of that collaboration to political and budgetary pressures. From a scientific standpoint, the Mars observations help address some of the questions about whether the brightness variations are real or artifacts of Earth-based observing. If the comet shows similar periodic behavior when viewed from Mars, from a completely different location, with different sampling patterns and instrumental effects, that strengthens the case that the periodicity is intrinsic to the object, not an illusion created by how we're observing it from Earth. Early indications suggest the patterns do persist from the Mars viewpoint, but the analysis is ongoing, and we need more detailed comparisons before drawing firm conclusions. The close approach to Mars also raises questions about whether the comet's trajectory might have been influenced by Martian gravity. At 12 million miles, the gravitational interaction is weak, but it's not zero. Precise astrometry, measuring exactly where the comet was before and after the encounter, could reveal tiny deflections in its path caused by Mars, and if those deflections don't match gravitational predictions, if there's unexplained acceleration or deceleration, that becomes another data point in the natural versus artificial debate. There's also been speculation about whether 3I-ATLAS might have posed any risk to Mars missions. 12 million miles sounds like a safe distance, and it is, but comets shed debris, and the dust particles in the coma can travel far from the nucleus. Could any of that material have reached Mars orbit? Could spacecraft have flown through the comet's dust trail? The answer appears to be no. The encounter wasn't close enough for that, but it's the kind of question mission planners have to take seriously. Impacting dust particles at orbital velocities can damage spacecraft, and there are procedures for protecting sensitive instruments or orienting spacecraft to minimize cross-sectional area during potential encounters. What the Mars observations really give us is context. 3I-ATLAS isn't just an object seen through Earth's telescopes. It's something witnessed by spacecraft across the inner solar system, tracked by rovers on planetary surfaces, observed from multiple angles with multiple instruments. This distributed observation network is how we build confidence in our findings, how we rule out instrumental artifacts, how we ensure that what we think we're seeing is really there. And it's a preview of what future observations might look like. If 3I-ATLAS continues deeper into the solar system, or if future interstellar objects arrive and pass close to our planets, we'll have more opportunities for multi-spacecraft campaigns, coordinated observations that maximize the science return. We might even design missions specifically to intercept such objects, to fly close enough to image their surfaces, sample their comas, measure their magnetic fields or radiation environments up close. That kind of mission is years or decades away, limited by technology and funding and the unpredictability of when and where interstellar objects might appear. But 3I-ATLAS is showing us that such objects do appear, they do pass through our solar system, and they're worth studying intensively when they do. The Mars observations are a proof of concept, demonstrating that we can coordinate international assets to observe transient phenomena, that we can get valuable data even from instruments that weren't specifically designed for comet studies, that we can adapt and respond when something interesting shows up. So while you're thinking about faint dots in grainy images from Mars orbit, remember that those dots represent something profound. They're photons that travelled from the Sun, bounced off an object that might have originated light years away, and were captured by cameras built by humans orbiting another planet. We're using tools we've scattered across the solar system to study a visitor from beyond, and in doing so, we're learning both about the visitor and about our own capabilities. And whether 3I-ATLAS turns out to be natural or artificial, that learning process, that expansion of our observational reach and our analytical sophistication is pushing us toward a future where we're better equipped to understand whatever the universe sends. Our way next. Part 12. Echoes of Oumuamua and Borisov, the Interstellar Family Album. 3I-ATLAS isn't the first interstellar visitor we've detected, and it won't be the last. To understand what makes it unusual, we need to put it in context with the other members of this small but growing family of objects from beyond our solar system. Let's talk about Oumuamua and Borisov, the two confirmed interstellar objects that preceded 3I-ATLAS, and what their differences might tell us about the diversity of things drifting through the galaxy. Oumuamua arrived first, discovered in October 2017 by the Pan-STARRS telescope in Hawaii. The name means scout, or messenger in Hawaiian, fitting for humanity's first confirmed visitor from another star system. From the beginning, Oumuamua was strange. Its light curve suggested an elongated shape, either cigar-like or pancake flat, with an extreme aspect ratio unlike any asteroid or comet in our solar system. It tumbled through space with a complex rotation, brightening and dimming dramatically as different faces caught sunlight. But the real mystery was its trajectory. As Oumuamua left the solar system, accelerating away from the Sun, astronomers noticed it was moving slightly faster than gravity alone could explain. Something was pushing it, giving it a tiny boost that changed its path measurably. For comets, this kind of non-gravitational acceleration is normal, caused by jets of gas erupting from the surface and acting like tiny rocket engines. But Oumuamua showed no signs of such jets, no visible coma, no dust tail, nothing that would indicate active outgassing. This led to a flurry of theories. Maybe it was outgassing something invisible, like hydrogen or nitrogen, that wouldn't show up in our observations. Maybe its shape was creating radiation pressure effects, sunlight pushing on its large surface area hard enough to account for the acceleration. Or maybe, as Avi Loeb famously suggested, it was artificial, a light sail or probe that was maneuvering using technology we couldn't detect. The debate hasn't been settled, and Oumuamua is long gone beyond the reach of our telescopes, carrying its secrets back into interstellar space. Then came Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. Unlike Oumuamua, Borisov looked like a comet. It had a coma, a tail, spectroscopic signatures of water and carbon monoxide and dust, all the things you'd expect from a normal comet. Its trajectory was clearly hyperbolic, confirming interstellar origin, but its behaviour was reassuringly ordinary. It rotated, it outgassed, it changed brightness, all in ways that matched our models. Borisov was proof that not every interstellar object is weird, that some of them are just comets from other star systems doing what comets do. The difference between Oumuamua and Borisov is striking. One defied explanation, the other confirmed expectations, and this tells us something important. Interstellar objects are diverse. They come in different shapes, different compositions, different activity levels. Just like the asteroids and comets in our own solar system vary wildly, so too do the objects wandering the galaxy. Some are rocky, some are icy, some are active, some are dormant. There's no single template for what an interstellar visitor should look like. Now enter 3I-ATLAS, which is neither fully weird like Oumuamua, nor reassuringly normal like Borisov. It looks like a comet, with outgassing and a coma and spectroscopic signatures that make sense. But it behaves with a precision that doesn't. It's got one foot in each camp straddling the line between the explicable and the mysterious. If you chart interstellar objects on a spectrum from completely normal to utterly baffling, Borisov sits at one end, Oumuamua at the other, and 3I-ATLAS lands somewhere in the middle, leaning toward the Oumuamua side the more we study it. This raises the question, are we seeing a continuum of natural objects with varying properties, or are we seeing a mix of natural and artificial objects and we're just not sure yet which is which? If 3I-ATLAS is natural but weird, that's interesting but not paradigm shifting. Nature is capable of surprising us, producing objects we hadn't imagined. But if 3I-ATLAS is artificial and Oumuamua was too, then we're not talking about rare anomalies. We're talking about a pattern, a suggestion that artificial objects in interstellar space might be common enough that we detect them once every year or two as our surveys improve. What we need, desperately, is more data. We need to detect more interstellar objects, study them with better instruments, capture high-resolution images and spectra, maybe even send spacecraft to intercept them before they leave the solar system. The Legacy Survey of Space and Time, LSST, which is scheduled to begin operations from the Vera Rubin Observatory, will dramatically increase the rate at which we discover transient objects, including interstellar visitors. Within a few years of LSST starting up, we might be detecting interstellar objects weekly or monthly, instead of once every few years. That influx of data will help us understand whether Oumuamua and 3I-ATLAS are outliers or representatives of a common class. We'll see whether most interstellar objects are comet-like or asteroid-like, whether periodic brightness variations are rare or common, whether non-gravitational accelerations are the exception or the rule. And if we start finding large numbers of objects with similar unusual properties, that becomes much harder to explain as coincidence. The family album of interstellar visitors is still sparse, just a few faded photographs in an otherwise empty book. But we're adding pages, and each new image tells us something about the diversity and abundance of objects, drifting through the cosmic ocean. Oumuamua showed us that interstellar objects can be profoundly strange. Borisov showed us they can be comfortingly normal. 3I-ATLAS is showing us they can be both at once, familiar enough to be catalogued as a comet, but peculiar enough to make us wonder if that catalogue entry is missing something important. And as we build this album, as we collect more examples and refine our understanding, we're also building a mirror. These objects reflect back at us our assumptions about what's natural and what's not, about what's possible and what's fantasy. They force us to question whether our models of solar system formation and comet behaviour are complete, or whether we've been working with an incomplete picture because we've only studied objects from our own little corner of space. They push us to consider whether the universe is simpler than we thought, full of similar objects everywhere, or more complex with processes and phenomena we haven't encountered yet. So tonight, when you think about 3I-ATLAS spinning through the dark, remember it's not alone. It's part of a growing family, a collection of wanderers that have passed through our solar system carrying stories from distant stars. Some of those stories might be tales of formation and evolution, written in the language of physics and chemistry. Others might be messages, intentional or accidental, from civilizations that looked up at their own skies and wondered if anyone else was out there. We don't know yet which category 3I-ATLAS falls into, but we're learning to read the language slowly, one visitor at a time, and that learning process, that gradual decoding of the stories written in trajectories and brightness curves and chemical compositions, is bringing us closer to understanding not just these objects, but our place in a galaxy that might be far more crowded and far stranger than we ever imagined. Part 13, Light Tricks in the Cosmos, Strange Reflectors Beyond Comets. Let's zoom out for a moment and talk about light, because the universe is full of objects that reflect or emit light in unexpected ways, and understanding those natural oddities is crucial before we decide something is artificial. 3I-ATLAS isn't the only thing in space that makes astronomers scratch their heads when they analyse its optical properties. There's a whole zoo of strange reflectors and emitters out there, and some of them are definitely natural, which should make us cautious about jumping to conclusions. Start with exoplanets. We've discovered thousands of planets orbiting other stars, and some of them have albedos, reflectivity values, that don't make sense based on what we know about planetary atmospheres and surfaces. There are hot Jupiters that are darker than charcoal, absorbing almost all the light that hits them, likely due to atmospheric chemistry that creates light-absorbing hazes. There are planets that are brighter than they should be, possibly because they're covered in reflective clouds of silicate particles or metallic compounds that scatter light efficiently. One particularly intriguing case is HD 189733b, a hot Jupiter that some researchers have suggested might have reflective clouds of corundum, the mineral that forms rubies and sapphires on Earth. If you had clouds of tiny corundum crystals high in a planet's atmosphere, they'd create optical effects unlike anything we see in our solar system, possibly including unusual polarization signatures or brightness variations that could be mistaken for artificial structures if we didn't know better. Then there are asteroids in our own solar system with surprising optical properties. Some asteroids have surfaces that are unusually bright or dark, way outside the typical range. Some show polarization curves that don't match standard models of dust scattering. In a few cases, these anomalies are so pronounced that early observers wondered if they might be seeing something artificial, metallic surfaces or geometric structures that were reflecting light coherently. One famous example is Apophis, an asteroid that will pass very close to Earth in 2029. Its surface properties are still being studied, but there are hints of unusual reflectance spectra that might indicate the presence of metals or minerals not commonly found on asteroids. Nobody thinks Apophis is artificial. It's clearly a natural object, but it shows how natural surfaces can create unexpected optical signatures when they have uncommon compositions or structures. In the realm of comets, there are several known cases of strange optical behaviour. Comet 2P/NK, for instance, shows periodic brightness variations that are more regular than most comets, related to its rotation and the distribution of active regions on its surface. It's not as precise as 3I-ATLAS, but it demonstrates that some degree of regularity can emerge naturally from the right combination of shape and activity. Comet Machholz 1 has an unusual composition, depleted in carbon chain molecules compared to typical comets, which gives it different spectroscopic properties. It's been suggested that Machholz might have formed in a different region of the solar system than most comets, or even that it could be an interstellar capture, an object from another star system that was gravitationally captured into an orbit around the Sun billions of years ago. If that's true, it shows that unusual chemistry alone isn't proof of artificial origin. Polarimetry has revealed that some asteroids have surface textures or compositions that create deep negative polarization branches similar to what 3I-ATLAS exhibits. These are often associated with objects that have experienced specific types of space weathering, or that are rich in certain minerals like olivine or pyroxene. The polarization anomalies can be dramatic, but they're explicable through natural mineralogy and surface physics. There's also the phenomenon of specular reflection from natural surfaces. Under certain conditions, if you have a smooth surface and the right viewing geometry, you can get mirror-like reflections that are much brighter than diffuse scattering. This has been observed on some icy moons in the outer solar system, where flat expanses of ice can act like mirrors when the Sun and observer are positioned just right. If 3I-ATLAS had regions of smooth ice on its surface, and those regions happen to be oriented favourably during part of its rotation, you could potentially get brightness pulses from specular reflection, without requiring engineered mirrors. Saturn's moon, Enceladus, provides another example of unexpected optical behaviour. The moon has geysers that erupt from its south polar region, ejecting water vapour and ice particles into space. These particles create a diffuse cloud around Enceladus that reflects sunlight and contributes to Saturn's E-ring. The brightness of the geyser plumes varies based on Enceladus's position in its orbit and the level of tidal stress driving the eruptions. It's a natural system, but it produces time-variable optical signatures that could be confusing if observed from a great distance without context. Moving beyond our solar system, there are stars that show brightness variations that initially seem like they might be artificial megastructures, Tabby's star, officially known as KIC 8462852, became famous in 2015 when astronomers noticed it was dimming irregularly, sometimes by as much as 20%, in patterns that didn't match eclipsing planets or any other standard explanation. There was brief speculation about alien megastructures, Dyson swarms or other constructs partially blocking the star's light. Years of follow-up observations have shown that Tabby's star's dimming is probably caused by dust, either from a disintegrating comet or from some more complex process we don't fully understand yet. The point is, nature can create optical signatures that initially look artificial, that trigger speculation about technology or intelligence, and then turn out to have prosaic explanations once we gather enough data. This history should make us humble when looking at 3I-ATLAS. The universe has shown us repeatedly that it's full of surprises, that nature is capable of creating structures and phenomena that seem too ordered, too regular, too purposeful to be random. And yet they are random, or at least natural, products of physics and chemistry operating under conditions we hadn't considered. But here's the flip side of that humility. Every time we find a natural explanation for something that initially looked artificial, we're also refining our understanding of what artificial would actually look like. We're learning to distinguish between the weird but natural and the genuinely anomalous. We're developing better intuition for what kinds of patterns nature can produce and what kinds require intervention. Tabby's star taught us that irregular dimming alone isn't enough to invoke megastructures. We need multiple lines of evidence, consistency across different wavelengths, absence of natural explanations, before we take artificial hypotheses seriously. Oumuamua taught us that non-gravitational acceleration can probably be explained naturally, even if the explanations require exotic ices or unusual shapes. Borisov taught us that most interstellar comets are probably normal, that the default assumption should be natural until proven otherwise. 3I-ATLAS is teaching us that regular brightness variations and precise rotation might be the signature we should watch for, the combination that's hard to achieve naturally and easier to achieve artificially. It's giving us a new set of criteria, a new template for what an artificial object trying to blend in might look like, and whether it turns out to be natural or artificial, that template will be useful for evaluating future discoveries. Because here's the uncomfortable truth. If artificial objects from other civilizations are passing through our solar system, they're almost certainly designed to look natural. Nobody's going to send a probe that screams alien technology from every observation. They're going to camouflage it, wrap it in ice, give it a trajectory that looks gravitational, make it outgas like a comet. The only way we'll ever recognize such objects is by noticing the subtle things that don't quite fit, the little inconsistencies that natural objects wouldn't have. And that means we need to understand natural oddities extremely well, so we can recognize when something crosses the line from merely odd to genuinely anomalous. We need to catalogue all the ways that natural objects can trick us, all the optical illusions and chemical surprises and dynamical quirks that nature is capable of producing. Only then can we confidently say that an object like 3I-ATLAS is behaving in ways that nature cannot, that it's showing us something genuinely new, possibly something that was made rather than born. So as you drift towards sleep tonight, remember that the universe is a hall of mirrors, full of reflections and illusions and things that look like what they're not. Our job is to learn which reflections are just tricks of the light and which ones might be signals from someone trying to get our attention. Part 14, the AI misinformation lesson, Tiago's retraction and beyond. Before we wrap up this journey through the mysteries of 3I-ATLAS, we need to talk about something uncomfortable, how easy it is to get things wrong in the age of artificial intelligence and instant information. This isn't ancient history, this happened during the same period we've been studying the comet, and it's a cautionary tale about the dangers of moving too fast, trusting too much, and letting enthusiasm override verification. Tiago, a science communicator with a significant online following, posted a live stream in late September 2025 discussing supposed bursts detected from 3I-ATLAS. According to his video, advanced AI analysis of telescope data had revealed periodic energy emissions from the comet, pulses of radiation that couldn't be explained by natural processes. The video went viral, racking up hundreds of thousands of views within days, sparking excited discussions across social media about whether we were witnessing the first confirmed artificial interstellar probe. There was only one problem. It wasn't true. The AI system that supposedly detected the burst had misinterpreted the data, seeing patterns that weren't there, or perhaps confusing signals from terrestrial sources with emissions from the comet. When other researchers tried to verify the findings using the same data, they couldn't reproduce the results. The burst didn't exist. To Tiago's credit, once he realized the error, he deleted the video and issued a public retraction. He explained what had gone wrong, acknowledged that he should have waited for peer review and independent verification before publicizing the claims, and apologized for contributing to misinformation. It was a responsible response to an honest mistake, and it highlights both the promise and the peril of using AI in scientific research. Artificial intelligence is revolutionizing astronomy. Machine learning algorithms can sift through enormous datasets, identifying objects of interest, classifying galaxies, detecting exoplanets, finding patterns that human researchers would miss or take years to discover. AI has made genuine contributions to our understanding of the universe, accelerating research and enabling discoveries that wouldn't have been possible with traditional methods. But AI systems are also prone to errors, especially when they're applied to edge cases or unusual situations. They're trained on existing data, and they learn to recognize patterns based on what they've seen before. When confronted with something genuinely new, something outside their training distribution, they can make mistakes. They might see patterns where none exist, or fail to recognize patterns that are genuinely there. And unlike human researchers, who can apply intuition and context and skepticism, AI systems lack the broader understanding necessary to sanity check their own conclusions. The Tiago incident isn't isolated. 2025 has seen several similar cases where AI-assisted analysis produced dramatic claims that didn't hold up under scrutiny. In March, a preprint appeared claiming that an AI system had detected evidence of room temperature superconductivity in a new class of materials based on analysis of crystal structure databases. The paper generated enormous excitement, making headlines worldwide before other researchers pointed out that the AI had essentially rediscovered known compounds with different names and misinterpreted their properties. The preprint was withdrawn. For 3I-ATLAS specifically, this raises important questions about how we validate the findings we've discussed. The Lomskargel periodogram analysis that detected the rotational period and brightness pulses is a mathematical technique, not an AI system, which gives it different strengths and weaknesses. It's less prone to the kind of pattern hallucination that neural networks can suffer from, but it still requires careful interpretation and validation. The fact that multiple independent teams need to confirm the periodicity before we accept it as real is precisely the safeguard that prevents AI-type errors from propagating. Science works through replication and peer review, multiple researchers examining the same data with different tools and assumptions, looking for consistency. When everyone sees the same signal, confidence grows. When some see it and others don't, that's a red flag suggesting either the signal is marginal or the analysis methods matter in ways we don't understand yet. The public's relationship with scientific claims has become complicated in the AI era. There's enormous appetite for breakthrough discoveries, for news that challenges our understanding of the universe. But there's also growing skepticism, fueled by repeated cases of claims that don't pan out, of exciting headlines that turn into retractions, of promises that fail to materialize. This creates a difficult environment for scientists trying to communicate ongoing research, trying to convey both the excitement of discovery and the uncertainty inherent in the process. 3I-ATLAS sits in that uncomfortable space. The data suggests something unusual is happening, unusual enough that it warrants serious study and public interest, but it's not conclusive enough to declare victory, to announce we've definitively found an artificial object or definitively ruled one out. We're in the messy middle phase of science, where different interpretations compete and evidence accumulates slowly, and certainty remains elusive. In this environment, the temptation to oversell findings is strong. There are incentives, professional and financial, to be first with dramatic claims, to capture public attention, to secure funding for follow-up work. But those incentives can lead researchers down dangerous paths, toward announcing results prematurely, toward downplaying uncertainties, toward letting hope corrupt the dispassionate analysis that science demands. Tiago's mistake, and his subsequent correction, is actually a model for how this should work. When you realize you've made an error, you acknowledge it publicly, you explain what went wrong, You remove the false information from circulation. You accept the temporary embarrassment in service of the longer-term goal of maintaining trust and accuracy. Not everyone does this. Some researchers double down on disputed claims. Some ignore criticism. Some quietly move on to other topics without ever acknowledging the problems with their earlier work. The broader issue is that science is getting faster, driven by automated telescopes, AI analysis, and instant global communication. We can go from observation to publication to worldwide news coverage in days or even hours. But speed is the enemy of careful verification. The traditional scientific process, with its peer review and replication and cautious language, evolved over centuries to filter out errors before they became accepted facts. When we short-circuit that process in the name of speed, we inevitably let more errors through. There's no easy solution to this. We can't go back to a slower era, and we wouldn't want to. The rapid pace of discovery is genuinely advancing our knowledge, and the ability to quickly share findings enables collaborations and follow-ups that wouldn't have been possible in previous generations. But we need to be smarter about how we communicate uncertainty, how we distinguish between preliminary findings and established facts, how we help the public understand that science is a process, not a series of definitive pronouncements. For 3I-ATLAS, the AI misinformation episode is a reminder to maintain healthy skepticism even as we explore exciting possibilities. The periodic brightness variations might be real. The positional shifts might be real. The chemical anomalies are definitely real. But the interpretation of what all this means, whether it's natural or artificial, whether it's a comet or a probe, that interpretation is still open, still contested, still requiring more data and more analysis before we can speak with confidence. And when that confidence comes, if it comes, it will be because multiple, independent lines of evidence all point in the same direction, because the natural explanations have been exhausted, because the artificial hypothesis, as uncomfortable as it might be, becomes the only remaining option that fits the data. Until then, we wait, we watch, we analyse, and we remember that the universe is under no obligation to make sense on our timeline, or to reveal its secrets quickly just because we're impatient to know. So tonight, as you think about everything we've discussed, from Russian astronomers breaking silence to Mars orbiters capturing images to AI systems making mistakes, remember that understanding takes time. The story of 3I-ATLAS isn't finished. We're still in the middle chapters, where the mystery deepens and the evidence accumulates, and the truth, whatever it is, remains tantalizingly just out of reach. That's uncomfortable, but it's also honest. And honesty, even uncomfortable honesty, is the foundation on which real science is built. Part 15. What comes next? Future missions, interceptors, and open mysteries. We've travelled through the evidence, examined the anomalies, considered both natural and artificial explanations for 3I-ATLAS's behaviour. Now it's time to look forward, to ask what comes next in our investigation of this object and others like it. Because whether 3I-ATLAS is a comet or a probe, it's shown us that interstellar visitors are real, they're detectable, and they deserve serious scientific attention. The European Space Agency's Comet Interceptor mission, currently scheduled for launch in 2029, represents our best near-term hope for studying an interstellar object up close. The mission's concept is ambitious. Instead of launching toward a specific target, it will position itself at a gravitationally stable point in space and wait. When a suitable target appears, a long-period comet or ideally an interstellar object, the spacecraft will activate, adjust its trajectory, and fly by the object at close range, capturing high-resolution imagery and analysing the composition of its coma and dust. This approach is necessary because we can't predict when or where interstellar objects will appear. By the time we discover them, they're usually already passing through the inner solar system, and there isn't time to design, build, and launch a dedicated mission. But a spacecraft waiting in the right orbit can respond quickly, reaching targets within months rather than years. Comet Interceptor will carry multiple instruments: cameras, spectrometers, dust analyzers, magnetometers, everything needed to characterize an object in detail during a brief flyby. If 3I-ATLAS were still going to be in the solar system in 2029, it would be an ideal target. But interstellar objects move fast, and by the time Comet Interceptor launches, 3I-ATLAS will likely be too far away to intercept. Instead, the mission will wait for the next visitor, or perhaps target a long-period comet from the Oort cloud as a backup. The data it returns will be invaluable for understanding what comets, whether interstellar or local, are really made of beneath their dusty surfaces. Beyond Comet Interceptor, there are concepts for even more aggressive interception missions. Some proposals envision rapid response spacecraft kept in storage on Earth, ready to launch on short notice when an interesting object is detected. These missions would use advanced propulsion, possibly nuclear, thermal or electric engines, to catch up with fast-moving targets. The engineering challenges are enormous. You need to predict the object's trajectory with extreme precision, launch at exactly the right moment, and have enough fuel to match velocities for detailed observations. But the payoff would be transformative. Instead of watching interstellar objects from millions of kilometers away through telescopes, we could send cameras within tens or hundreds of kilometers, close enough to see surface features, to distinguish between natural and artificial structures, to sample the coma directly and analyze its chemistry with laboratory precision. A single close flyby of an object like 3I-ATLAS would answer more questions than years of remote observations. NASA has studied similar concepts under various names over the years. The Bridge program, proposed in the early 2020s, would have developed technologies for fast response to interstellar objects. Budget constraints kept it from moving forward, but the ideas remain viable, waiting for the right combination of scientific opportunity and political will. If 3I-ATLAS continues to show anomalous behavior, if the artificial hypothesis gains more traction, you can bet that funding for interstellar object interception will suddenly become available. On the ground and in Earth orbit, telescopes continue to improve. The Vera Rubin Observatory, with its legacy survey of space and time, will begin operations soon and will revolutionize our ability to detect transient objects. LSST will image the entire visible sky every few nights, cataloguing everything that moves or changes. The survey is expected to discover tens of thousands of asteroids, hundreds of comets, and potentially multiple interstellar objects per year once it reaches full operation. This increase in detection rate will give us the statistics we desperately need. Is 3I-ATLAS unusual among interstellar objects, or typical? Do most of them show periodic behavior, or is this rare? What's the distribution of compositions, shapes, activity levels? With dozens or hundreds of examples instead of 3, we'll be able to identify patterns to separate the genuinely anomalous from the merely uncommon. The James Webb Space Telescope continues to observe comets and asteroids when its schedule permits, bringing infrared sensitivity that ground telescopes can't match. Webb can detect organic molecules, measure temperatures, map the distribution of ices across a comet's surface. If 3I-ATLAS remains within Webb's reach for the next year or two, we can expect detailed spectroscopic follow-up that will further constrain its composition and activity. Radio telescopes, particularly the Very Large Array, and newer facilities like the Square Kilometre Array, when it becomes operational, offer another avenue for investigation. Even if 3I-ATLAS isn't broadcasting intentionally, it might emit radio waves through natural processes like molecular transitions in the coma, or possibly through interactions with the solar wind. And if it is broadcasting, even weakly, sensitive radio observations could detect signals that optical telescopes would miss entirely. The upcoming observational campaigns will focus on several key questions. First, does the periodicity persist as the comet moves farther from the Sun? Natural rotations can change as comets heat up or cool down, as outgassing patterns shift, as structural changes occur. If 3I-ATLAS maintains its 4-hour rotation and 2-hour brightness pulse with the same precision for months or years, that strengthens the case for something unusual maintaining the stability. Second, are there spectroscopic features we haven't noticed yet? With higher resolution and better signal-to-noise ratios, astronomers might detect trace molecules or unusual isotope ratios that provide clues about the object's origin or nature. Industrial processes, if this were artificial, might leave signatures in the form of unusual isotope abundances or molecules that don't form naturally in space. Third, can we detect any changes in trajectory that can't be explained by gravity and natural outgassing? Precise astrometry, measuring the comet's position to milliarc-second accuracy over long baselines, might reveal tiny accelerations consistent with course corrections. This is difficult, requiring years of data and sophisticated modelling to separate genuine trajectory changes from measurement errors and natural forces. The philosophical angle becomes important here. What do repeating patterns in space tell us about the universe? Natural laws themselves are patterns, regularities that emerge from the fundamental physics governing matter and energy. The fact that planets orbit stars in ellipses, that atoms emit light at specific wavelengths, that radioactive decay follows exponential curves, all of these are patterns that we might misinterpret as design if we didn't understand the underlying mechanisms. But some patterns require specific initial conditions, specific arrangements of matter that are unlikely to arise by chance. A crystal has a regular structure, but it forms through natural processes wherever conditions are right. A computer chip also has a regular structure, but it requires intentional assembly. Couldn't form naturally even given billions of years. The question for 3I-ATLAS is which category it falls into. Is its precision the precision of crystal formation, natural order emerging from simple rules? Or is it the precision of a microchip, order imposed by intelligence? This is where citizen science becomes valuable. Amateur astronomers around the world are tracking 3I-ATLAS, contributing observations to international databases, helping to fill in gaps in the coverage that professional observatories leave. With modern equipment, amateurs can measure positions and brightnesses with respectable accuracy, and their geographic distribution means someone is always watching, even when major observatories are closed by weather or daylight. So as we close this investigation, as you prepare to let sleep carry you away from these cosmic mysteries, let me leave you with a final thought. 3I-ATLAS has shown us patterns we cannot ignore. The 4-hour positional shift, the 2-hour brightness pulse, the chemical anomalies, the optical peculiarities, each one individually might be natural, but together they form a picture that refuses to come into focus. Whether it is a masterclass of natural mechanics, the galaxy's most perfectly balanced snowball, or a message we're not yet ready to decode, the universe is whispering secrets, and our instruments are finely sophisticated enough to hear the whisper. We don't know yet what those secrets mean. We don't know if we're alone or surrounded by ancient probes watching us from the darkness. We don't know if 3I-ATLAS is the exception or the rule, the first confirmed visitor, or just the first one we've noticed. But we're listening now, we're watching. And whatever comes next, whatever 3I-ATLAS ultimately reveals about itself and about the universe that sent it, we'll be ready. Because that's what we do. We look up, we wonder, we ask questions, and we refuse to stop searching for answers until the universe finally decides we're ready to hear them. Sleep well. The cosmos will still be there in the morning, spinning its mysteries, waiting for us to unravel them one careful observation at a time.